Yes, it is indeed a requirement to ground the metal exterior shell of a building that has one. NEC Section 250.4a mandates that all exposed metal surfaces of electrical equipment that are likely to become energized must be connected to the grounding terminal or enclosure of the equipment. This requirement explicitly includes the metal frames of buildings. Moreover, NEC Section 250.118 stipulates that metal enclosures of electrical equipment must be grounded. This provision encompasses the metal exterior shell of a building if it is utilized as an electrical enclosure. The fundamental reason behind these requirements is to ensure electrical safety and prevent potential hazards. By effectively bonding the metal frames of a building to the service ground, a low impedance path is established. This path allows fault current to swiftly and safely flow back to the source. This rapid clearing of fault current is crucial for several reasons. Firstly, it minimizes the duration of a fault, reducing the potential for damage to equipment. Secondly, it significantly lowers the risk of electrical shock to personnel who may come into contact with the metal structure during a fault condition. In essence, grounding the metal exterior shell provides a vital safety mechanism that protects both individuals and the building's electrical system. The grounding system serves as a protective measure. In the event of a fault, such as a live wire coming into contact with the metal shell, the fault current needs a path of low impedance to flow back to the source, which is typically the transformer. This low impedance path allows a large amount of current to flow quickly, tripping the circuit breaker or blowing the fuse, thereby de-energizing the circuit and preventing a prolonged shock hazard or fire. Without proper grounding, the metal shell could become energized, posing a significant risk to anyone who touches it. The code requirements are not merely suggestions, they are carefully crafted safety standards based on years of experience and research. They are designed to minimize electrical hazards and ensure the safe operation of electrical systems. Failing to comply with these requirements can have serious consequences, including fines, legal liabilities, and most importantly, the potential for injury or death. The grounding system typically consists of several components working together. Firstly, there is the grounding electrode, which is a conductive rod, plate, or other object buried in the earth to provide a direct connection to ground. Secondly, there is the grounding electrode conductor, which is a wire that connects the grounding electrode to the service equipment, such as the main electrical panel. Thirdly, there is the equipment grounding conductor, which is a wire that connects the metal enclosures of electrical equipment to the grounding system. These components work in harmony to create a comprehensive grounding system that protects against electrical faults. When installing a grounding system, it is crucial to follow the requirements of the NEC. This includes using the correct size and type of grounding conductors, properly bonding all metal parts together, and ensuring that the grounding electrode is properly installed. Failure to comply with these requirements can compromise the effectiveness of the grounding system and increase the risk of electrical hazards. There are several methods to accomplish the grounding and bonding of the metal exterior shell. One common method is to connect the metal frame to the main grounding busbar in the electrical panel using a properly sized grounding conductor. This connection ensures that the metal frame is at the same electrical potential as the ground, minimizing the risk of voltage differences and electrical shock. Another method is to use bonding jumpers to connect all the individual metal components of the exterior shell together. This creates a continuous conductive path that helps to equalize the electrical potential throughout the structure. In addition to grounding and bonding the metal exterior shell, it is also important to ground and bond all other metal parts of the building that are likely to become energized. This includes metal conduit, metal junction boxes, and metal enclosures of electrical equipment. By grounding and bonding all these metal parts together, a comprehensive grounding system is created that provides maximum protection against electrical hazards. The size of the grounding conductors used to ground the metal exterior shell must be determined in accordance with the NEC. The size of the grounding conductor depends on the size of the service entrance conductors. The larger the service entrance conductors, the larger the grounding conductor must be. This is because the grounding conductor must be able to carry the maximum fault current that could flow in the event of a fault. In addition to the size of the grounding conductor, It is also important to ensure that it is properly installed. The grounding conductor must be securely connected to the metal exterior shell and to the grounding system. It must also be protected from physical damage. If the grounding conductor is not properly installed, it may not be able to carry the fault current effectively, increasing the risk of electrical hazards. Regular inspection and testing of the grounding system are essential to ensure that it is functioning properly. Grounding systems can deteriorate over time due to corrosion, physical damage, or improper maintenance. Regular inspections can identify potential problems before they become serious hazards. Grounding tests can verify that the grounding system is providing a low impedance path for fault current to flow back to the source. These tests can identify problems such as loose connections, corroded conductors, or inadequate grounding electrodes. If any problems are found, they should be corrected promptly to ensure the continued safety of the electrical system. In summary, grounding the metal exterior shell of a building is a critical safety requirement that must be followed to protect personnel and equipment from electrical hazards. The NEC provides detailed requirements for grounding and bonding metal structures, and it is essential to comply with these requirements to ensure the safe operation of electrical systems. Regular inspection and testing of the grounding system are also important to ensure that it is functioning properly. Always consult with a qualified electrician or electrical engineer to ensure that the grounding system is properly designed and installed. Proper grounding and bonding is not just about meeting code requirements, it is about protecting lives and property. By taking the necessary steps to ensure that electrical systems are properly grounded and bonded, a safe environment can be created for everyone. Ignoring these requirements can have devastating consequences. The NEC is updated regularly to reflect the latest advancements in electrical safety and technology. It is important to stay up to date on the latest code requirements to ensure that electrical systems are installed and maintained in accordance with the current standards. The NEC is a complex document, and it can be challenging to understand all the requirements. If there are any questions about the code, it is best to consult with a qualified electrician or electrical engineer. They can provide guidance on how to comply with the code and ensure that electrical systems are installed and maintained safely. Grounding and bonding are essential components of a comprehensive electrical safety program. A well-designed and properly installed grounding system can significantly reduce the risk of electrical hazards and protect personnel and equipment from harm. It is an investment in safety that pays dividends in the form of reduced risk and increased peace of mind. So, when designing or installing electrical systems, always prioritize grounding and bonding to ensure the safety of everyone involved. Remember that electricity can be dangerous, but by following the code and taking the necessary precautions, it can be used safely and effectively. The principles behind grounding relate to impedance. Impedance is the measure of opposition that a circuit presents to the flow of alternating current. It extends the concept of resistance to alternating current circuits and includes both resistance and reactance. Reactance is the opposition to current flow due to inductance and capacitance. In a grounding system, low impedance is crucial. The lower the impedance of the grounding path, the more effectively it can conduct fault current back to the source. A high impedance grounding path can impede the flow of fault current, potentially preventing the circuit breaker from tripping and increasing the risk of electrical shock. Grounding also helps to stabilize voltage. In an ungrounded system, voltage fluctuations can occur due to imbalances in the load or due to static electricity. Grounding provides a reference point that helps to stabilize the voltage and prevent these fluctuations. This is particularly important for sensitive electronic equipment that can be damaged by voltage fluctuations. Grounding and bonding are often used interchangeably, but they are not the same thing. Grounding refers to connecting electrical equipment to the earth, while bonding refers to connecting different metal parts of a building or structure together. The purpose of bonding is to create a continuous conductive path that helps to equalize the electrical potential throughout the structure. This prevents voltage differences from occurring between different metal parts, which can reduce the risk of electrical shock. Bonding is typically accomplished by connecting all the metal parts together using bonding jumpers or other approved methods. The NEC provides detailed requirements for bonding, including the size and type of bonding conductors that must be used. The proper installation of grounding and bonding systems requires a thorough understanding of the NEC and other applicable standards. It is essential to follow the code requirements carefully to ensure that the system is functioning properly. It is also important to use high-quality materials and to employ qualified electricians who have experience in grounding and bonding. The cost of a properly designed and installed grounding and bonding system is a small price to pay compared to the potential cost of an electrical accident. Electrical accidents can result in serious injury or death, as well as property damage and legal liabilities. By investing in a quality grounding and bonding system, these risks can be significantly reduced. Grounding is essential for surge protection. Surges are transient overvoltage events that can damage or destroy electrical equipment. They can be caused by lightning strikes, power grid switching, or other events. Grounding provides a path for surge current to flow safely to the earth, protecting equipment from damage. Surge protective devices, or SPDs, are often used in conjunction with grounding to provide comprehensive surge protection. SPD are designed to divert surge current away from sensitive equipment and towards the grounding system. Grounding also plays a role in electromagnetic compatibility, or EMC. EMC refers to the ability of electrical equipment to operate without causing interference to other equipment. Grounding helps to reduce electromagnetic interference, or EMI, by providing a path for unwanted currents to flow to the earth. This can improve the performance and reliability of electrical equipment. When designing a grounding system, it is important to consider the specific requirements of the application. The type of equipment being grounded, the location of the equipment, and the potential for electrical hazards all need to be taken into account. A qualified electrician or electrical engineer can help to design a grounding system that meets the specific needs of the application. The NEC provides specific requirements for grounding different types of equipment. For example, there are specific requirements for grounding electrical services, grounding separately derived systems, and grounding equipment in hazardous locations. It is important to consult the NEC to ensure that the grounding system complies with all applicable requirements. Regular maintenance is essential to ensure that the grounding system continues to function properly over time. Grounding connections can loosen or corrode, reducing their effectiveness. Regular inspections can identify potential problems before they become serious hazards. Grounding tests can verify that the grounding system is providing a low impedance path for fault current to flow back to the source. The effectiveness of a grounding system can be affected by the soil conditions. Soil with high resistivity can impede the flow of current to the earth. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to use special grounding techniques to achieve an acceptable grounding resistance. There are several different types of grounding electrodes that can be used, including ground rods, ground plates, and concrete encased electrodes. The type of grounding electrode that is best suited for a particular application depends on the soil conditions and the available space. Grounding and bonding are essential for telecommunications systems. Telecommunications equipment is particularly sensitive to electrical surges and interference. Grounding and bonding help to protect telecommunications equipment from damage and to ensure reliable communication. The NEC provides specific requirements for grounding and bonding telecommunications systems. These requirements are designed to minimize the risk of electrical hazards and to ensure the proper operation of the telecommunications equipment. Grounding and bonding are also important for renewable energy systems, such as solar and wind power systems. Renewable energy systems can generate significant amounts of electrical power, and it is essential to properly ground and bond these systems to protect personnel and equipment from electrical hazards. The NEC provides specific requirements for grounding and bonding renewable energy systems. These requirements are designed to ensure the safe and reliable operation of these systems. In addition to the NEC, there are other standards that may apply to grounding and bonding systems. For example, the IEEE STD 142, also known as the Green Book, provides guidance on grounding electrical systems. It is important to be aware of all applicable standards when designing and installing a grounding system. Proper grounding and bonding is essential for electrical safety. By following the code requirements and taking the necessary precautions, a safe electrical environment can be created for everyone.